July 1st, 2025. Astronomers spot what looks like an ordinary blip, only to realize it's an interstellar comet plunging through our solar system at 130,000 miles per hour, potentially as large as Manhattan. Then, the real shock. New images and data reveal this visitor, 3I/Atlas, is unleashing more carbon dioxide than any known comet, with leading scientists debating if its chemical fingerprint is even natural, or if we could be looking at evidence of alien technology. The story behind these new 3I/Atlas images has upended everything we thought we knew about cosmic intruders, and what comes next will force us to question what exactly just entered our celestial neighborhood. At 3:11 a.m. UTC on July 1st, 2025, the ATLAS survey software flagged a fast-moving object in the southern sky. At first, it looked like just another routine detection, one of thousands of faint blips the system catalogues every night. The initial data, logged at the Rio Hurtado station in Chile, showed a dim speck drifting against a crowded starfield. But within minutes, the automated pipeline registered something unusual. The object's apparent motion was off the charts, clocked at over 130,000 miles per hour. For comparison, that's more than double the speed of most near-Earth asteroids flagged by the network. The ATLAS team, led by survey operators on the night shift, scrambled to verify the result. The software's first pass had flagged the target as a possible main belt asteroid, but the velocity didn't fit. A quick check of the time-stamped images revealed a streak longer than expected for any slow-moving object at that distance. The Rio Hurtado telescope's detection was soon confirmed by a second ATLAS unit, and then by the Zwicky Transient Facility at Palomar. Each independent measurement told the same story. This was no ordinary solar system body. Within hours, the object's sky position was relayed to observatories worldwide. Follow-up teams ran the numbers, calculating the trajectory with increasing precision. The math was clear. The object's hyperbolic path and blistering speed meant it wasn't gravitationally bound to the sun. It was inbound from interstellar space. The initial misclassification was quickly scrubbed from the logbooks. In its place, a new designation, 3I/ATLAS, the third confirmed interstellar visitor ever recorded. What began as a nondescript dot buried in a sea of data had, in a matter of hours, triggered a global alert. Survey operators who spend their nights chasing false alarms now found themselves at the center of a discovery that would soon dominate headlines. The ATLAS hardware designed for planetary defense had just caught a messenger from another star system, moving so fast that every minute counted. The race to characterize this cosmic intruder had begun. Within minutes of the confirmation, the astronomical community sprang into action. Darryl Seligman, working from Michigan State, fired off a global alert that rippled through professional networks and amateur channels alike. Every major facility with a clear line of sight, Chile, Hawaii, South Africa, Australia, scrambled to reprogram their schedules. The object's speed, 130,000 miles per hour, left no time for debate. Observatories that usually wait months for a slot now dropped everything to chase a fast-moving target that could vanish from reach in days. The size estimates only added to the urgency. Early readings suggested a nucleus somewhere between 3.5 and 12 miles across, possibly the largest interstellar object ever detected, but with uncertainties so wide that even seasoned comet hunters hesitated. Was this a Manhattan-sized chunk of ancient ice, or just a smaller body surrounded by a deceptive coma? No one could say for sure. The only way to find out was to capture as much data as possible from as many angles as possible before the opportunity slipped away. Coordination became a logistical marathon. Seligman's team relayed coordinates to the Minor Planet Center. Automated alerts pinged robotic telescopes across both hemispheres, triggering a rolling cascade of observations as night swept around the globe. Instruments that usually hunt for exoplanets or track variable stars were redirected to capture the intruder's brightness curve, rotation period, and spectral fingerprints. Within 48 hours, the object's motion had been logged by over a dozen facilities, each feeding their results into a constantly updated database. The pace was relentless. As the comet raced toward the inner solar system, teams in Europe and Asia picked up the baton, filling in gaps left by clouds or daylight elsewhere. Amateurs with backyard setups joined the effort, uploading images and astrometric positions that helped refine the orbit. Every new data point narrowed the uncertainty, but the true nature of the object remained elusive. With the clock ticking, the focus shifted to securing time on the most powerful instruments, those capable of dissecting the comet's light and revealing its chemical secrets. The world's attention had locked onto a single, fast-moving speck, and the scientific chase was officially on. The James Webb Space Telescope's first look at 3I/Atlas delivered a number that left comet scientists stunned. The infrared spectrum, captured on August 6, 2025, showed carbon dioxide spiking so high that it overwhelmed every other volatile in the coma. The measured carbon dioxide to water ratio was 8:1. For context, most comets in our solar system have carbon dioxide levels that barely register next to water, usually less than 20%. Here, water wasn't just outnumbered, it was nearly drowned out. Webb's team, led by Martin Cordiner, ran and reran the analysis, checking for calibration errors, stray light, anything that could explain the outlier. But the result held up at a confidence of 4.4 sigma, statistically ironclad, far beyond the realm of random chance. The carbon dioxide line strengths in the NIR spec data were so pronounced that even the most skeptical team members had to admit there was no mistake. This wasn't a trick of the instrument or a misfire in the pipeline. The spectrum lit up with the unmistakable fingerprint of carbon dioxide, dwarfing the water vapor signal to a degree never before seen in a comet. Cordiner, who had dissected the chemistry of 2I/Borisov and dozens of solar system comets, called the finding unprecedented. To put this in perspective, the only other comet to come close was C/2016 R2 Pan-STARRS, an outlier in its own right, but even that one didn't reach Webb's numbers. In statistical terms, 3I/Atlas sits 6 standard deviations above the average for solar system comets. That's not just rare, that's off the charts. What could drive such an extreme ratio? Theories began to circulate. Maybe 3I/Atlas formed near a carbon dioxide ice line, or perhaps its surface had been baked by radiation so long that water was locked beneath a crust. But no one could point to a solar system object that looked quite like this. The chemistry wasn't just odd, it was alien, in the most literal sense. Webb's data forced the scientific community to confront the possibility that 3I/Atlas came from a planetary nursery radically different from our own, and with every line in the spectrum, the mystery deepened. SphereX, freshly commissioned in May 2025, turned its attention to 3I/Atlas within weeks of the comet's discovery. Its infrared spectrometers swept across the object's coma in early August, capturing a spectral fingerprint that echoed what Webb had just found. Carbon dioxide everywhere you looked. In fact, SphereX mapped a carbon dioxide gas coma stretching nearly 350,000 kilometers from the nucleus, far wider than the visible dust envelope seen in optical images. Notably, the spectrograph's data revealed almost no water vapor in the gas phase, only faint signatures of solid water ice embedded in dust grains. This pattern, dominant carbon dioxide emission, subdued water vapor, and strong water ice absorption, matched Webb's readings line for line. Ground-based observatories joined the chase. NASA's Infrared Telescope facility on Mauna Kea, the Gran Telescopio Canarias, and the Nordic Optical Telescope all reported the same story. The infrared continuum was swamped by carbon dioxide, with water ice features present, but water gas nearly absent. The dust coma, measured in the near-infrared, showed a continuum slope and brightness profile that fit the carbon dioxide-driven activity model. Even the coma's spatial structure, mapped in the infrared, matched the scale of the carbon dioxide envelope seen by SPHERICS. Across the globe, teams compared their results. Spectra from Chile, Hawaii, and Spain were overlaid with SPHERICS orbital scans. Every dataset showed the same sharp carbon dioxide bands, the same lack of water vapor emission, and the same dust-to-gas ratio. This was no fluke of a single instrument or a calibration error. The chemical anomaly was real. Every facility, every wavelength, every method confirmed it. With each independent observation, the case for an interstellar comet with extreme carbon dioxide dominance grew stronger. The chemical puzzle was locked in place. The world's telescopes had for the first time watched a visitor from another star system reveal its secrets, and the evidence was unanimous. Nickel lines, sharp and unmistakable, began to appear in the Very Large Telescope's spectra of 3I/Atlas as it drew closer to the Sun. But something was off. The expected iron lines, normally a partner to nickel in cometary comas, were nowhere to be found. Thomas Puzia's team in Chile ran the numbers again. The result held: nickel was present, iron was missing. In comet science, that's like finding the tracks of one boot in fresh snow, but not the other. Nickel without iron had never been documented in a comet, interstellar or otherwise. The data revealed more. The nickel was in atomic form, not locked up in dust grains, and its abundance changed dramatically as the comet moved inward. Production rates for nickel, calculated from the VLT's high-resolution spectra, followed a steep curve, Q of Ni scaled as the heliocentric distance to the power of -8.4. For cyanide, another volatile, the curve was even steeper, nearly -9.4. These numbers pointed to an activation process far more complex than simple heating. Something was releasing nickel atoms efficiently, while iron stayed hidden. The absence of iron, despite the detection of its usual companion, forced researchers to consider new chemistry. One possibility: nickel is being released from organometallic compounds, perhaps nickel tetracarbonyl, which breaks apart easily under ultraviolet light. But that would require formation conditions or radiation processing not seen in solar system comets. Another idea: the parent body formed in an environment with an unusually high nickel-to-iron ratio, a signature of its birth cloud or the residue of ancient stellar explosions. Both options pushed the boundaries of known cometary chemistry. Puzia summed up the puzzle: "We just cracked open the door to a whole new world of chemistry that we never had access to before." The nickel mystery added a new layer to the 3I/Atlas enigma, suggesting that the processes shaping its metals are unlike anything catalogued in comet science. With every new spectrum, the object's chemical story grew stranger, hinting at pathways of metal release and molecular assembly that challenged the standard models. The comet wasn't just a messenger from another star system, it was a laboratory for reactions never seen on Earth. The path traced by 3I/Atlas through space is more than a curiosity. It's a message from a time before the Sun even existed. Astronomers tracking its trajectory found themselves looking far beyond the familiar orbits of comets born in our neighborhood. Instead, the numbers pointed back to the Milky Way's thick disk, a population of stars formed when the galaxy was young and restless over 7 billion years ago. This isn't the thin, orderly disk our solar system calls home. The thick disk is older, rougher, and metal-poor, a fossil record of the galaxy's formative years. To confirm the connection, researchers ran orbital integrations, winding the comet's path backward through millions of years of gravitational nudges and galactic tides. The results were striking. 3I/Atlas didn't just wander in from the local suburbs. Its velocity, direction, and orbital inclination all matched the signature of thick disk objects. Ancient wanderers launched into the void when the Milky Way's chemistry was still primitive. The odds of a random interstellar object matching these parameters by chance are vanishingly small. The age estimate is just as staggering. Statistical models anchored by the thick disk star formation history suggest a birth date more than 7 billion years ago, twice as old as the planets circling our sun. That means 3I/Atlas, condensed from a disk of dust and gas, when the Milky Way was still assembling its spiral arms, during an era astronomers call cosmic noon. Back then, radiation fields were harsher, and the building blocks of planets contained fewer heavy elements. The comet's chemistry, dominated by carbon dioxide stripped of water, bears the scars of that environment. David Jewitt, who has spent decades studying the oldest bodies in the solar system, calls 3I/Atlas a time capsule from the galaxy's youth. He points out that while telescopes can image distant galaxies as they were billions of years ago, this is the first time a relic from that era has drifted within reach. The comet's journey, spanning half the age of the universe, offers a direct sample of conditions that shape the earliest planetary systems. Its presence in our skies is a reminder that the solar system is not an isolated oasis, but part of a galaxy where ancient objects still roam between the stars. Harvard astronomer Avi Loeb has not shied away from controversy, and 3I/Atlas gave him new ammunition. He points to the comet's retrograde orbit, tilted 175 degrees, just 5 degrees off the ecliptic, as a statistical oddity, calculating that such a precise alignment should occur in only 2 out of every 1,000 random arrivals. Loeb argues that this trajectory, combined with the comet's size and brightness, makes it a candidate for something more than a natural object. He's even suggested that a retrograde near-ecliptic path could allow an advanced probe to efficiently observe or deploy toward multiple planets during a single flyby. But the evidence tells a different story. NASA's teams have logged weeks of continuous monitoring, and every major observatory, from Hubble to JWST to the VLT, reports the same thing. 3I/Atlas is active, volatile-rich, and unmistakably cometary. There are no artificial signals, no anomalous accelerations, and no unexplained energy sources. The coma glows with carbon dioxide, water, and nickel, exactly what you'd expect from a body forged in the cold outskirts of a planetary system, not a machine built by alien engineers. Skeptics in the planetary science community point out that a retrograde near-ecliptic orbit is rare, but not impossible. The Sun's motion through the galaxy and the geometry of interstellar arrivals can naturally produce alignments like this, especially as more visitors are catalogued. As for the size, Hubble's sharpest images set the nucleus diameter at no more than 5.6 kilometers, large for an interstellar object, but well within the range for natural comets. The debate over 3I/Atlas's origin may draw headlines, but the data are clear. Extraordinary claims demand extraordinary evidence. In this case, the evidence all points to a natural origin. A comet, ancient and alien only by virtue of its birthplace, blazing through the solar system on a path written by gravity, not intention. The James Webb Space Telescope is scheduled to turn its gaze back toward 3I/Atlas in December 2025, this time after the comet has rounded the Sun. The goal is to track how the chemistry and dust activity change as solar heating peaks and then fades. Hubble will take its turn in November, using ultraviolet spectroscopy to probe the comet's gas emissions and hunt for sulfur-bearing molecules, clues to the ancient chemistry locked inside. Meanwhile, the Vera Rubin Observatory, now fully operational, is expected to spot dozens more interstellar visitors each year, making 3I/Atlas the first in what could become a steady stream of galactic messengers. Each mission brings its own strengths. The James Webb Space Telescope's infrared spectrographs can pick apart faint molecular bands, revealing how the comet's volatile inventory evolves after perihelion. Hubble's sharp imaging and UV sensitivity will help nail down the composition of the coma and the ratios of key elements. Rubin's survey cadence means that even the briefest interstellar flybys are now within reach, allowing astronomers to build a population-level picture of these ancient travelers. More than a dozen observatories worldwide are coordinating to follow 3I/Atlas as it recedes, watching for any late surprises in brightness or outgassing. Every new data point adds to the global effort, a patchwork of light curves, spectra, and orbital updates, all feeding into a growing archive. The next year promises a rush of fresh insights as the world's most advanced telescopes chase the fading trail of a visitor that began its journey before our sun was born. 3I/Atlas entered the record books on July 1st, 2025, moving through our solar system at over 130,000 miles per hour. Its carbon dioxide to water ratio of 8:1, measured by JWST and confirmed by SphereX, remains one of the highest ever seen in any comet. Spectra revealed atomic nickel without iron, and orbital modelling traced its origin to the Milky Way's thick disk, suggesting an age nearly twice that of our solar system. NASA and independent analyses agree there is no evidence of artificial origin, despite public debate fueled by its retrograde orbit and size. Yet key questions remain. Why is carbon dioxide so dominant? And what processes shaped its exotic chemistry? As 3I/Atlas continues its journey, upcoming observations by JWST Hubble and the Vera Rubin Observatory will test current models and may rewrite what we know about planetary building blocks. For now, 3I/Atlas stands as a rare messenger, older than Earth, reshaping our understanding of both cosmic history and the possibilities within interstellar space.